on the reverse bias should be modeled by this combination of circuit elements. Its beginning breakdown voltage with Z0 in series with this small Zener resistance. The whole combination is representing the actual Zener diode. Because RZ is non-zero, so the full voltage drop at the Zener diode is the beginning breakdown voltage VZ0 plus additional voltage drop across this resistance RZ. And you can see if the input voltage has variation, then the input current has variation. The input current part of it diverted to the Zener diode, so the Zener current has variation. So if the Zener current has variation, then the full Zener voltage has variation, which means your low voltage is not constant, which is also true if the the demand on the current change. If the low current change, then the current amount that we can directly into the Zener diode also change, and leading to the load voltage changing as well. So that's a real, okay, the actual Zener diode has a finite resistance. Now we'll do the full analysis. How do we analyze this circuit? And this circuit is, you can see that it's one of the simplest circuit you may analyze in 306. And the DC circuit, and we just use a node voltage method to analyze this circuit. So this is the reference ground. This top node is a node. So if this current subtract this, putting in this current equals this current plus this current. So the II input current equal the current go to the Zener diode plus the load current. And the street current can be expressed as this voltage subtract the load voltage divided by this resistance gives you this current. And load voltage subtract this VZ naught, that's the actual voltage drop across the RZ, and divide the resistance gives you the Zener current, which is the first term on the right hand side. And the second term on the right hand side is just load current. So we derive this equation by node voltage method. And this one is I want the output voltage, which is VL, which is dependent on the dependent on the source voltage VPS, so which is rearranged in this term, and depends on how much load current we use. IL is here. So it's a simple arrangement of the expression in this equation. We can arrange into this equation. And further, I rearrange it, pull out the VZ naught really out as first term. And then I add VZ naught, then I subtract VZ naught. Once I subtract VZ naught, the whole term can be expressed in the second combination in this way. So we can see, if power supply voltage VPS has variation, directly influence the load voltage VL. If the load current has variation, it also leads to variation of load voltage, right? This is a mathematical expression of what we allude on the initially qualitatively in this graph. Now further, there are two types of variations with distinction. One is cost variation caused the power supply voltage. Another one coming from the load current. The first way to quantify the regulation, how good it is called source regulation. In source regulation, what we assume is we have a constant load current. So load current IL is constant, fixed. However, the source voltage VPS varies. So IL is constant, doesn't change, but the VP change. And this VP change directly leads to the change of VL. So the VL, delta VL equals this proportional coefficient times the change of power supply voltage VPS. So that's this equation. And the ratio of delta VL over delta VPS is this one, plus V4 converted into the percentage you times 100%, and that defines source regulation. So this first is the definition, okay? It's the exact definition. But the result we derived the early equation, when we rearrange it, it is really the distance is equal to RZ divided by RI plus RZ. Okay, so how good regulation is? Actually, how big do you want this number be large or small? Actually, you want this large number be small. Basically, you may have some sort of a sizable change of your power supply voltage, but you really want to have a minimum impact on the output voltage. So this quantity should be as small as possible. What's the extreme? How small it can go? Only if the Zener resistance is 0. If Zener resistance is 0, yes, we have a source regulation be 0%. It means output voltage or the low voltage doesn't change no matter how you change the input voltage. However, for non-ideal Zener diode, the RZ is non-zero, so you have a finite fraction here. Okay, that's a limit to say compared to the ideal Zener diode to non-ideal Zener diode. There's a second type of way to characterize or measure how good the regulation is. It's called the load regulation. In load regulation, then we assume the input source voltage doesn't change, it's fixed. However, load changes. For example, load current changes. So now we calculate the two quantities. One quantity is called the output voltage or the low voltage, VL, but under condition for no load. What does it mean low load? Basically, you disconnect the load here. Once you disconnect the load here, then the load current is 0. So IL is 0. No load really means load current is 0. Okay, previously we derived this equation. If you set the load current is 0, so remove the last term. Once you remove the last term, the rest is the load voltage under no load. That's first term, this one, plus the second term of this portion, re-expressed here, right? So that's under the zero load current. We have this, load voltage. Well, the other extreme is we have a maximum load current. So that means IL takes the value of IL maximum. So take IL maximum. So that rewriting here. So in writing here, really you compare these two expressions, you can see the second expression is this portion exactly equals to the first one, which is a V low under no low. So I'm rewriting here. And the last term in the bracket, this one, times this fraction, the coefficient in front of it, is the remaining term here, right? So I can write the load voltage under full load condition equals load voltage under zero load current condition plus additional term. And the difference between the no load the voltage and the full load voltage, I call the delta L. So delta L really is responsible becoming, this coefficient, Ri times Rz divided by Ri plus Rz, this one, and times the range of load current, we apply to the load. So that's just say how load current variation can cause low voltage variation. So expressed in this expression. And the formal definition of the load regulation is the voltage difference between the no load to full load normalized by the full load voltage and converted into percentage, times 100%. So these two formal definition of regulation due to the source or due to the current, load current. Any questions? No question? So go to the next page and take example. So this example saying this is our source, and this source voltage VPS can range from 11 volts to 13.6 volts. So we have a non-ideal okay, source, okay, not constant. And we may have running this situation, the load current has variation. So what's the range of the load current variation? It range from 0, that's no load, to maximally equals to 100 milliamps. So that, okay, we may run into a situation load current can change. And what we want is, we want the low voltage, okay, the VL, be as stable as possible to a nominal level, okay, of 9 volts. So we want VL equal to 9 volts. Well, we know input voltage is non-ideal, not constant, but we want to stabilize the load voltage equal to 9 volts. So what do we do? And our gut feeling is we'll select the Zener diode, the reverse breakdown voltage equal to 9 volts. So we'll select the Zener diode voltage, the breakdown voltage equal to 9 volts. That's our initial gut feeling, the selection. However, what I'm claiming is, even we want to select the Zener diode, the breakdown voltage is 9 volts. Unfortunately, the real Zener diode comes in with a Zener resistance, let's say, for example, equal to 10 ohms. 10 ohms is a pretty small resistance. And in 306, okay, the circuitry perspective, we almost think about that's trivial, almost nothing. But here I want to point out that the 10 ohm Zener resistance, well, play a role, influence the Zener, okay, voltage regulator circuit. And here also the finite, the input resistance Ri, let's take the value of 15.3 ohms. Okay. Now we know the source voltage can vary in the range. And so, okay, low current also has a variation in this range. Now we can evaluate the two types of regulation. One is source regulation, okay, output voltage, low voltage only caused by change of the input voltage. And previous calculations say that's given by this formula. So you plug in the Zener resistance equal to 10 ohms, divided by the input resistance 15.3 ohms plus Zener resistance 10 ohms. You calculate this ratio, turn out to be 11.6. Okay. So that's reasonably good. Basically saying, even you have some voltage change in input voltage, but the low voltage change only be 11.6% of your input voltage change. So it's deduced by approximately factor of 9. How about the load regulation? The load regulation, then, as we said earlier, the input voltage is constant. And here, for a specific example calculation, we just claim the the input voltage is as maximum value. So VPS maximum means the input voltage equal to 13.6 volts. Okay, just assuming input voltage is stable at this peak level, 3.6 volts, but low current can change. So low current change, first case, zero low current, low load. So that's a formula we derived early, is this expression. You plug in the value of VZ0 9 volts, and plug in the value of RZ 10 ohms, plug in the value of RI equal to 15.3 ohms, and this VPS equal to VPS maximum equal to 13.6 volts, and again, VZ naught equals to 9 volts. Complete this calculation gives you 9.532 volts. Yes, we want to stabilize 9 volts, but in reality, actually we get a 9.53 volts. This 9.53 volts is under condition the load current is 0. How about the load current to the full maximum current equals to 100 milliamps? We evaluate the load voltage by the second formula. Well, we already calculate this quantity equal to 9.532 volts, and we can evaluate this quantity, okay, based on the load current equal to 100 milliamps. They'll reduce by small amount to 9.355 volts. And you plug in these two quantities, into this formula to evaluate called the load regulation. So it's 9.532 minus 9.355 normalized by 9.355, and which gives you 1.89%. It's much better. Okay. So let's just give you the in reality. Okay, you use a Zener diode to further want to stabilize your regulated voltage source. Well, we can do that. Okay, further improve. However, we just cannot do it as perfectly as we wish. Any question? Okay. So formulas derived and examples given, and today I will assign another homework. Okay, problem set. Okay, a problem is related to Zener circuitry. Okay, you can practice that. If no question, okay, let's talk about the last one. Last one is
Professor?
Yes, please.
I'm sort of confused of what what's the goal here? What does this circuit do as a function?
Oh, focus on this part circuitry. The first part. So first part is the source circuitry. This source circuitry coming from what do we say? The rectified circuit. Rectified circuit is bumpy, and we even use a low pass filter to smooth it out, but it still has a ripple. You see this point? It's not a perfect DC voltage source. It has a ripple. So this has a ripple voltage, VPS. So we want to use a Zener diode to further stabilize this ripple or reduce the ripple. Do you get it? Do you understand the purpose?
So then which is VL the input and VZ is the output?
No. You got it. What do you mean by input and output? Read this circuitry. This is your source. Say you use wall plug to get your pulse, okay, DC convert into DC voltage source. That DC voltage source has a ripple. This is your load. This is your iPhone, or this is whatever your tablet. Why you read VL is a source? No, this is the source. Source voltage applied to the load, but the source voltage has a ripple. That means your load voltage has a ripple. That's not ideal, or that's not good. We want to further stabilize the load voltage, and we apply the Zener diode, try to stabilize this load voltage further. Clear? Hello?
Okay, that makes some more sense.
Right? VL is not a source. VL is end result. We apply the source voltage to the load. If the source has variation, the low voltage has variation. We don't want that. So your device designed as powered by the 9 volts. You want the load voltage remain as 9 volts. So that's why you use a Zener diode circuitry to further stabilize the load voltage. Okay? And previously we described the input voltage variation can cause a load voltage variation. We also described low current variation can cause a low voltage variation. Now there's another situation saying, okay, we change the load, but changing load is not directly coming from the low current, but because the load resistance change. Okay, this is another possibility. Okay, so that just say here, variation of the power supply voltage or load. The load all could coming from load current or load resistance. So the next page describe what if we know the load resistance change. Okay, what if we describe the load variation is from the variation of the load resistance. The mathematical equation still is the same, okay? Is this equation we derived early, and I repackaged them into a standard load voltage method. So VL minus the VPS divided IRI. So this is a VL minus this voltage divided this resistance, and this voltage subtracted this voltage divided by this resistance plus this voltage divided this resistance. So this is a standard no voltage method. You know the 306 stuff, you can derive this equation easily. So once I put in equation in this form or derive the equation in this form, okay, I put all the terms related to the load voltage to the left-hand side and the rest terms to the right-hand side. Rest term in the right-hand side all are constant. So suppose the load voltage, the input voltage is fixed, and this right-hand side is 0. So what you can see is that if the resistance change, load resistance change, then right-hand side is constant. So if RL change, VL should change. Only thing is we need to figure out they change in what direction. So you look into this circuit here. If load resistance is minimum, if load resistance is minimum, it means what? It draws the maximum amount of load current. Okay. If you draw the maximum amount of load current, then the current we can deliver into the Zener diode IZ will be reduced. Okay, so the load current is maximum, then the Zener current actually is minimum. When Zener current is minimum, then the Zener voltage will be minimum. Zener voltage will be minimum. And the Zener voltage exactly equal to load voltage because this component and that component are connected in parallel. If the Zener voltage is minimum, then the low voltage is minimum. So this low voltage minimum. So I have a typo written in the uploaded PDF file. So previously this equation says that VC minimum equal to VC minimum. You can say, oh, what's that? That's trivial, right? That's not what I meant. So this is correct. So the Zener voltage minimum really means at the same time the low voltage is minimum. So when the load resistance is minimum, then the low voltage is minimum. The other extreme opposite is if the load resistance is maximum, what's the maximum? Infinity. Okay. If the load is a maximum resistance, so the load current is minimum. So the IL is minimum. IL is minimum. That means the input current mostly will go to Zener diode. So the IZ will get a maximum. IZ will get a maximum.
Professor,
Yes.
why does the circuit for the non-ideal Zener voltage regulator circuit not have a Zener diode in it? Am I missing something?
Yes, you missed something. Okay. Good. Okay, you raised that question, so I would remind you what you missed. Okay. You missed this page. You need to really digest. Okay. The book is a thick book. I try my best to put down the most important part of information. Oh, I didn't have that into slides. Okay, let's see. You basically, so we went through that slide in chapter 1, but it looks like some part content in chapter 1.
Professor,
Yes.
are you expecting us to be able to see that window you just opened?
No. I have not loaded up yet. So here now I load up because I have to load in the chapter 1 slides. Okay. So be patient a little bit. I'm loading, but it takes some time. So this is chapter 1 slide. Okay. So what your part of missing or that your memory was not very strong on which part? So I'm referring you back to chapter 1 contents. Okay. Chapter 1 contents. It's this part. Do you see this? On the left. Page 31.
Yes.
Zener diode, this is Zener diode is a circuit symbol. But what we are saying is we know we want most of the time we operate the Zener diode under reverse bias, not reverse breakdown situation. So what do we characterize the reverse breakdown? So the Zener diode can be modeled by a constant step-down voltage VZ0 in series with RZ. That's the thing I want you to memorize.
So we're modeling it as a resistor and a voltage source?
Yes.
Does this assume a particular, this assumes that current is flowing that direction through the diode?
Yes, assuming,
Always?
yes. The Zener current is pointing from this side to this side. Yes, Zener current going this way, and Zener voltage is defined as plus minus. So this IZ is the same as this IZ. This full Zener voltage is this is full voltage VZ here.
Okay. Sorry, that just surprised me that we're using that as the non-ideal because voltage sources and resistors are linear and Zener diodes are non-linear. So when it said non-ideal, that confused me.
No. This non-ideal Zener diode refers to RZ of non-zero. Okay. Well, if you're not still confused, I have to refer you back to this slide, even further. Page 25. Did you digest the material in this slide? When we say ideal diode is in many different ways. Regular ideal diode has certain terminology. It's this one, ideal diode. Okay, that's referred regular ideal diode. But the Zener ideal diode is referring to we're not operating the full bias. We are not operating a regular reverse bias. We are operating on the reverse breakdown. You have to describe this current voltage relationship for Zener diode. How do you describe this straight line? How do you describe this straight line mathematically? This straight line is exactly described by this formula. Exactly described by this formula. Okay? And this formula means what? The full Zener voltage contains a constant step breakdown voltage VZ0 plus, if we visualize there's a Zener resistance in series with this step down voltage, then there's additional voltage drop by Ohm's law by the second term described here. Are you clear? That's a realistic Zener diode.
So is this an approximation of a Zener diode, or is a Zener diode genuinely made from... I understand this is an approximation, but it seems like you're saying this is the declarative formula. Is this declarative or is this approximation?
So it all depends on your view which part. Okay. The Zener breakdown is you have a finite finite reverse bias current going the red line, it became reverse breakdown. If anything physical reverse breakdown, there's a little bit run up, right? So this corner is not strictly sharp. It's slightly reverse breakdown and then pick up. So there's a finite corner here, correct? Any physical device, there's a finite turnaround, right?
So we're modeling a Zener diode as if it's always in breakdown voltage.
At this beginning, yes, right from here.
And also that it's linear, because that is almost a straight line, but the equation that has e to the power ups and whatnots would tell us that that's slightly not, right?
No. It is, which part? This is a straight line. Only straight line says what? It doesn't apply to this small corner. But we operate the Zener diode not nearly the turnaround point. We operate the Zener diode mostly in this region. That's a straight line. What's your question? So if you say exactly plotting, you have to trace this red line. Yes, this part modeling this straight line. Okay, we can say describe the Zener current voltage relationship in this region, not around the corner, in the vast majority region. Any question? And here, if you want back one more slide I use, okay, here I can comment on this. Piecewise linear model, okay, we approximate the accurate nonlinear current voltage relationship that's in the forward direction, but actually this statement can also be said to the reverse breakdown situation. So we say use several linear relationship. In this case, I show two relationships. One is a forward, bias diode turn on. One is turned off. That's two. If you count in the Zener, they have a third line here. Okay. So the several depends on you want to use visualize two is diode on, diode off. Then if you want to expand this 2 to 3 to include the Zener reverse breakdown, then you have another curve, straight curve, shoot here. Any question? Did I answer your question? Hello? Okay.
Yeah, you can go on. I'm sorry, I'm not following.
I have to watch my time. Okay, so the full. Can you imagine this straight line if we use piecewise linear model? Yes or no? Hello?
No, I'm sorry. I think we're misunderstanding each other. I was just confused of why this was a non-ideal analysis of the circuit as opposed to an ideal one. I'm wondering. I followed this.
Ideal for the point is when you apply this ideal, refer to what? Why I say it's not ideal Zener diode? It's not ideal Zener diode means what? If the ideal Zener diode, this straight line is vertical. If non-ideal, this straight line has a finite slope. It's only referred to that sense. It's within the reverse breakdown region. How do you describe ideal, not ideal? Okay? It has its own definition. Okay? Zener diode. Where's the Zener diode? Sorry. Ideal or not ideal means if RZ is 0, the Zener diode on the reverse breakdown is ideal. It breaks down at just a single point. If non-ideal, then the larger you have get the Zener current, then the Zener voltage change a little bit. That's non-ideal. Only in that concept. Any question? You don't want to confuse this with the regular diode under forward bias in that sense. For that, then you mix two operation regimes. Any question? No question? Let's go to further. So the next circuitry, okay, we want to study is a caliper circuit. Okay, so first looking for the example. This simple circuitry, this input voltage could be standard, okay, sinusoidal or square wave or any waveform and so on and so forth. We're just using a sinusoidal wave to representing the input voltage. And the rest circuitry is a resistor R and have a diode, regular diode, and jack up by a DC voltage source, V battery, and so on and so forth. In this analysis, we use as we said, we always from here on using the piecewise linear model. And the simplified further, we say that the forward resistance under turn-on condition is RF equal to 0. RF equal to 0. Okay. And I mentioned before, in the piecewise linear model, okay, when you're near the diode's threshold point, diode current is 0, okay, or almost 0. If a diode current is 0, if this current is 0, that means the current passing through the resistor is 0. So the voltage drop at the resistor, we can neglect. So VR, I neglect almost 0. If the voltage drop at the resistance be almost neglect, then the diode voltage will be the voltage difference between the input voltage and the battery voltage. So VI minus VB. So I'm able to link the diode voltage to the input voltage and battery in my circuit. Of course, when diode voltage greater than V gamma, means VI minus VB greater than V gamma, diode is on. And VI minus VB greater than V gamma can be rewritten as VI greater than VB plus V gamma, diode is on. Now, once diode is on, what's the consequence? There's a constant voltage drop, VB, and when diode is on, there's constant voltage drop, V gamma there. Okay, constant voltage drop V gamma is because we assume the simplest situation, the forward resistance is 0. So the output voltage VO just equal to VB plus V gamma. So that's under condition diode is on. When the input is above this level, if you flip this inequality sign to the other way, when the input voltage is less than this amount, sure, diode should be off. When the diode is off, then you can sort of think about this open circuit here, the output voltage just strictly coming from the input voltage. VO equal to VI. So this mathematically we derive the result, and this graphically we plot the result. So the input voltage, suppose let's say sinusoidal, and we identify one important or critical level, VB plus V gamma, which is this level. When input is above this level, which means that this region time duration, the output is constant at VB equal to V gamma. When input is below this level, which means that this region, the output duplicate the input. So the output duplicate input. What's the output? Really, it's input voltage, but the top is clipped. So this is a clipper circuit or limited circuit. Any question? So question, okay, let's go to the second example. Second example, okay, say the input source resistance R is the same, and we have 2 diodes and 2 batteries. Okay, one diode D1 and VB combination is very similar to the previous configuration. Okay, so the previous configuration is a diode and battery voltage, diode, battery voltage. Okay, polarity-wise, direction-wise, the diode is connected exactly the same. However, we use also the second diode, the second battery voltage connected the other way. So the polarity VB is plus is at the bottom here, a minus terminal, and the direction of the diode is a flip. compared to diode 1. Okay, D2 direction of the diode is flipped compared to diode 1. So now we analyze this circuit. Okay, we add additional branches here. Well, behavior for this branch is exactly the same as when we use the previous configuration. So that means, well, here before that, let's just say, important step is that I always want to figure out what voltage influence the diode voltage D1 and influence diode voltage D2. Diode voltage D1, VD, equal, if I neglect the voltage drop at the R, at the threshold point, so equals the input voltage minus the voltage VB1 gives you VD1. So that's this equation. How about the diode voltage D2? That means I have to use this side voltage, subtract this side voltage. What's this side voltage? It's minus VB2, is this point. And what's this side voltage is VI. So it's a minus VB2 minus a VI is voltage drop at VD2. VD2 is a plus here, minus here, that's VD2. So I'm able to express the dependence of VD1 to VI and VB1, the diode 2 voltage VB2 dependent on VB2 and VI. Of course, when VD1 greater than V gamma 1, diode 1 is on. When diode is on is when input voltage is during the positive cycle. The positive cycle, D1 is forward bias. Obviously, D2 is reverse bias. D2 is off. And D1 greater than V gamma 1 can be rewritten as substitute into this expression into D1, rewritten as VI above D1 plus V gamma 1. And their output voltage, if once D1 is on, the voltage drop is VB1 plus V gamma 1. The first part of the result is exactly the same as what we said previously. Now we turn to the other way. The other way is what? If input is during its negative cycle, if the input during the negative cycle, D1 is a reverse bias. On the other hand, D2 is forward bias. So D2 forward bias when D2, VD2 greater than V gamma 2. And VD2 is given by this expression. If this expression is greater than V gamma 2, I can rewrite that inequality into this form. D2 is on. When D2 is on, diode 2 is on, what's the output voltage? Output voltage is VB2, step down, VB2, and further step down V gamma 2. So output voltage equal to minus VB2 minus V gamma 2. Okay. So I have two conditions, have two outcomes. But what if both conditions are not, neither condition is not satisfied? So I have to flip this inequality sign. I have to flip this inequality sign. I get the last one combined. So VI is ranging between VB1, V gamma 1, and minus VB2, V gamma 2. Both sides off. Both sides off, the output strictly gets to output strictly coming from the input. V out equal to VI. So I have three situations, three output waveform. Now, let me plot this output waveform. Okay, these mathematical equations, okay, let's see graphically what it looks like. So there's one important level, VB1 plus V gamma 1 is a positive set here. There's another important level, minus VB2 minus V gamma 2 is set here. When the input voltage is above the level 1, important level 1, the output is clamped at VB1 and V gamma 1. So clamped here, clamped here. If the input voltage is below the second important level, so in this region, the output is clamped here and there. In between, output follows input, so just the rest of the sine wave will from this region that region, this sinusoidal, sinusoidal, sinusoidal. So we can see this circuit clipped both the top and bottom. So it's a double clipper or double limiters. Any questions for the clipper circuit? Okay, so this is another functionality of a diode circuit, clipper circuit. Let me give you another example. So this configuration, okay, now the location of the battery and diodes change around and so on and so forth. Okay, don't be scared. Let's step by step, okay, do the analysis. As I said, the first important thing is, okay, figure out what influence the diode voltage VD. Or the other way to say is, can I express mathematically diode voltage in terms of the input voltage or in terms battery voltage in the circuit? I want to relate the VD voltage. VD actually equals VR in the other way. VD voltage related to VI and VB. How do I calculate VD? So I have to use the positive side, the voltage, subtract the negative side voltage. Positive side voltage sits at 0, or I reference this point as ground, 0. So that's 0. That's this side voltage, I call it 0. So what's this side voltage? This side voltage is the voltage VI, step down VB. So it's VI minus VB. So it's VI minus VB. You may ask, do you have to consider voltage drop at the resistance? Well, my claim is near the threshold point, I neglect that. So it's approximation. So this is the claim I'm making. Okay, remember always. Near diode's threshold point, okay, diode current is negligibly small, and then the voltage drop at the resistance can be neglected. Okay, simplify the analysis, or simplify the critical point, the analysis. So at the critical point, diode voltage is given by this expression. So when this voltage VD greater than V gamma, diode is on. Once diode is on, what's output voltage? Well, once diode is on, there's a constant voltage drop V gamma. So output voltage is minus V gamma. So under condition diode on. If this condition, the inequality is reversed or not satisfied, means our input voltage is greater than VB minus V gamma, then diode is off. Once diode is off, what's output voltage? Once diode is off, you can visualize this as a break, open circuit. The output voltage coming from input voltage VI, but step down by amount of VB. So output voltage equals VI minus VB. So I derive the mathematical outcome equations under two conditions. Under two conditions, is judging by input is below this level or input is above this level. So an important level is called VB minus V gamma. So here is VB minus V gamma. So the black is the sinusoidal input voltage. I identify the important level VB minus V gamma at this level. Now I'm looking for first result I derive is what? If the input is below this level, so input is below this level means what? This portion, and this portion input. For this portion input, what's output voltage? Output voltage equal to minus V gamma. So I label it minus V gamma. Output voltage is here, constant. If input voltage is above this level, so input voltage is above this level, so this portion and this portion. So what's output voltage? Output voltage shape-wise follows the input, but the level is downshift by the battery voltage. So I'm just redrawing this portion downshift by VB. So that's this red curve. So overall, this red curve is output voltage. Any question? Okay. You may notice that, okay, this circuitry I hand drawn myself. And what I want to comment is that this example is given in the textbook. And textbook assume V gamma equal to 0. Okay. And give an output plotting. And that output plotting is incorrect, misleading. So forget that output drawing for this example. Okay, use my drawing. Any questions? Okay. And you notice that in the 3 examples I use, this textbook example, the diode has a finite voltage step down, V gamma. So V gamma is a non-zero, V gamma is a non-zero. In this case, V gamma is non-zero, V gamma is non-zero. And even in this example, I say V gamma is non-zero. Okay. In the homework, quite a number of the homework assume V gamma equal to 0. I don't like that. So in the homework problems, okay, many homework problems I refer to chapter 2, but I specify condition. I will ask TA to also say that. Okay, we always assume V gamma is non-zero. So you have to work out V gamma equal non-zero, you solve the diode circuit accordingly. Any question? No question? Now let's learn next important circuit called the clamper circuit. So this clamper circuit is a source diode, but important thing is we introduce a capacitor. So in the clamper circuit, capacitor play an important role. Let's see how the role played out by the capacitor. So again, input is sinusoidal. We assume the forward resistance is non-zero, but it's zero, it's zero, but the V gamma is non-zero. Initially, visualized capacitor is discharged. So initial capacitor voltage is 0. So always can assume we start from this condition. How diode voltage is influenced by rest voltage? In this configuration, this is diode voltage. So it's a VI minus VC is the voltage at the top. Subtract voltage at the bottom, that's the diode voltage. VD equal to VI minus VC. When VD greater than V gamma, when VD greater than V gamma, and here I said VI, is because what? We assume the capacitor voltage is 0. So diode voltage just equal to input voltage. When input voltage is greater than V gamma, diode is on. Once diode is on, now we have a complete loop circuitry. And this complete loop says the source voltage can charge the capacitor. So diode is on, capacitor is charging. Capacitor charging, what's the capacitor voltage is charging to? Then is a input voltage subtract diode voltage, which is V gamma, is the capacitor voltage. So the VC equal to VI minus V gamma. When VI gets to the maximum, VC gets to the maximum. And this graph shows capacitor voltage is charging from 0 to its peak. When capacitor charging the peak, it's because input gets to the peak. But once input reaches the peak, it starts to roll off, lower. Once it come across the top, becomes smaller, then the diode becomes off. Once diode becomes off, then you can see what's the configuration. Can you discharge the capacitor? No way, because diode is off, this open circuit, capacitor has no way to discharge. So capacitor voltage remain constant at the peak level. So that's indicate this. In a steady state, when we say after initial transient, so for the rest part of circuit, then capacitor voltage remains constant. So what's the output? Translate output is what? The input voltage subtract the constant capacitor voltage gets the output. So the input voltage subtract a constant capacitor voltage which equals at maximum gets output voltage. So it's the input voltage waveform downshift by this amount. So output voltage is shift from input voltage by constant level, but keep the same waveform. There's no clipping occur, only shifting the output voltage from input by constant level. So this clamp circuit, the other way to say is what? The top level of the circuit is clamped at some level. In this case, it's clamped at V gamma. Okay. Okay. During this process, or in the steady state, okay, what's the state of diode? So to answer that question, I have to go back to say, determine the diode voltage. Diode voltage equals what? Actually, diode voltage equals to input voltage subtract this capacitor voltage, which gives the diode voltage. Or diode voltage, in this case, equals output voltage. Output voltage given in this expression, that's diode voltage. Okay? And you're substituting the VC maximum, which is given by this expression. Finally, I have a VI minus VI maximum plus V gamma. Okay, so I have this expression. In this expression, the first two terms combined always is okay, 0 or less than 0, or negative number. A negative number add to V gamma, so this altogether is less than V gamma. So diode voltage is always less than V gamma. So diode remains off. So that's clamp circuit. Any question? So question, let's work out another example. This example, okay, we have more components. We throw in another resistance and put a voltage in a different location. Put another low voltage source, battery source here. It looks a little bit complicated, but analyze this step by step. Again, this example, I modify that so that I use a finite V gamma. So this drawing is different from textbook. So let's do the complete analysis. Again, I want to express diode voltage in terms of the rest voltage. What determines diode voltage? What determines diode voltage is what? The input voltage, VI. And if there's voltage drop at the capacitor with polarity plus minus, so input voltage minus capacitor voltage, I get the top. The bottom is the battery voltage. Difference gives you the diode voltage. So VI minus VC minus VB is diode voltage. And initially, we always assume capacitor discharge, the voltage is 0. So initially, capacitor voltage is 0. So when VI minus VB greater than V gamma, or VI greater than VB plus V gamma, diode become on. Diode become on, then capacitor can charge. Because this is 0 resistance, capacitor will charge in this way. Capacitor charging. Capacitor charge, what's the capacitor voltage? Is this voltage minus this voltage. What's this voltage? It's VB plus V gamma. So capacitor voltage equals VI minus VB minus V gamma. So if input voltage gets maximum, capacitor voltage gets maximum. Again, capacitor will charge maximum. But once the input voltage rolled off from the peak, diode becomes off. In this configuration, when diode is off, we just break this path. However, there's another path for current to complete. So this input source through the capacitor, through the resistor, through the battery, there's another loop allow the current to flow. Once you have another current allowed to flow, what happens is that you really start to discharging the capacitor. But here, when we construct the clamper circuit, we set some condition. We set that the capacitor and resistor values sufficiently large, or particularly say, we select the value of a capacitor very large, make that RC time constant very large. When RC time constant very large, the capacitor is discharging, but only discharging very slowly. But when it's slowly, it means the capacitor voltage barely unchanged, barely changed, so it remains mostly unchanged to the maximum. So this condition always pretty much remains true. So in a steady state, if a capacitor voltage almost remains constant, the input voltage minus capacitor voltage leads to output voltage. Again, is input voltage shifted by a constant voltage drop at the capacitor. A similar analysis, we can analyze the diode state. Diode state is diode voltage. In here, diode voltage does not equal the output voltage. So really, you have to figure out the output voltage. So you can have two different ways to derive. We derive the output voltage. So the output voltage minus the VB gets the diode voltage. So what do you have? So the output voltage is this guy. This one. Minus the battery voltage, this one, is the diode voltage. And you substitute the expression of a capacitor voltage maximum by this expression, you get a final form in this form. Again, this form says what? First two terms combined never can be positive, 0 or negative. And you combine with V gamma, it's always be less than V gamma. We prove diode voltage in a steady state is always less than V gamma, diode remains off. So in clamper circuit, once reached to the steady state, diode becomes off or under reverse bias, always under reverse bias. Any question? Okay, question. Let's looking for another circuit. Okay. This circuit is a transformer circuit, like in the bridge configuration. However, here we only use 2 diodes instead of 4 diodes. In place of the other 2 diodes, I put in 2 capacitors. And sometime, at some point, capacitor will get a charge. And if there's capacitor voltage drop, I define the polarity voltage is plus VC2 plus minus here, VC1 plus minus there. Okay. Capacitor voltage VC1 polarity, VC2 polarity, VC1 polarity, VC2 polarity. Again, important thing is we want to determine what influence diode voltage. Diode voltage VD1. So what's this diode voltage be influenced? That influenced by what? VS input voltage. And if you subtract VC2, that's VD1. So VD1 equal to VS minus VC2. How about VD2? So what's this voltage drop? This voltage drop is equal to this voltage difference subtract this voltage. Or this reference point, you have a minus VS, you have a minus VS minus VC1 gives you VD2. So VD2 equal to minus VS minus VC1. Okay. Initial condition, 2 capacitors are discharged. So when input voltage is greater than V gamma 1, because initial voltage capacitor is 0. So when this voltage greater than V gamma 1, diode 1 on, diode 1 on. When diode 1 is full bias, of course, diode 2 is a reverse bias. Diode 2 is off. When diode 1 is on, what's the current path? Current path is this loop, diode 1 can go here, charging capacitor 2. Okay, so we're charging the capacitor 2. You can charge the capacitor 2, so what's the voltage drop charge the capacitor? Is input voltage Vs minus the constant voltage V gamma 1 is a VC2. So VC2 is Vs minus V gamma 1. And Vs get maximum, and Vc2 charge maximum. The negative cycle is everything reverse. So basically, minus Vs plays the same role as Vs, but acting on Vd2. So condition is revised into when Vs is less than minus V gamma 2, diode 2 is full bias on, diode 1 is reverse bias off. Now we're charging capacitor C1. Okay, capacitor current C1. So Vc1 equals to minus Vs minus V gamma 2. So what's minus Vs? You reference from this point, and this point is a minus Vs. Minus Vs minus, this minus Vs minus V gamma 2 gives you Vc1. So Vc1 equal to minus Vs minus V gamma 2. Basically, we're saying in the negative cycle, minus Vs plays the same role as Vs when the gamma diode 2 replaces the role of diode 1. So rewriting this equation by minus Vs minus V gamma 2. And when during the negative cycle, when Vs get to the minus Vs, then everything becomes positive Vs maximum. Okay, because Vs itself is a negative, that negative maximum, you multiply by additional plus minus sign, then it turns into the Vs maximum. So that's capacitor 1 also charges this amount. In the steady state, so what's the voltage drop across the load reference between this point to this point? Okay, that's just a Vc2 plus Vc1. Vc2 plus Vc1 together. And substituting these two expressions, we get a Vs maximum minus V gamma and twice of that. So that's voltage doubler. Okay. In the textbook's example, again, it assumes V gamma equal to 0, so you have a 2 times Vs maximum. But if you include the role played by the finite drop of V gamma, then V gamma is placed in this location. That's V gamma here. So this voltage doubler. So sinusoidal input voltage by the transformer step down, Vs is still sinusoidal. But if you use a capacitor, then you can we can charge the capacitor full maximum. And when we say in some cycle we discharging, but discharging, we choose the capacitor value is so large, discharging very slowly. So when slowly, then capacitor voltage almost become constant nearly at its peak, and that it becomes a peak constant voltage we produce across the load. So this is voltage doubler circuit. Any question? Okay, question. So let's go to a few other diode circuit. One is a photodiode detector circuit. How do you construct the circuit? Is a diode, photodiode means once you shine in a light, the diode property change. In this circuit, the diode should be reverse bias. Once reverse bias, at least in the dark condition, means no light shining in, the diode is under reverse bias, there's no current. Or the current is a dark current we can neglect because of reverse bias. Things change when you shine the light. When you shine the light produces electron and hole pairs, as I described early in the chapter 1. Okay, once by the breaking down the covalent bonds in the space charge region, you produce a lot of carriers and then produce large current. So important things is in this circuitry, diode must be reverse biased. An LED circuit is a connection, say for example, the digit, the 7 segment digit. So then you have 7 LED elements, D1 through D7. You need to bias this in a 4 bias configuration. On the triangle side, all connect to the plus voltage plus 5. On the other side, through a resistor, you limit a certain amount of current. Then you connect to the control voltage VI, and VI1, VI2, VI3, and to the VI7. Okay, so VI is control voltage, K means a case dial. These are control voltages. Obviously, if any one of the control voltages, say VIK, is 0, and this is 5 volts, this is 0, is 4 bias, dial is on. Dial is on, then it eliminates light. Okay. Then if the control voltage, J is control voltage, this element is set to equal 5 volts. This side is 5 volts, this side is 5 volts. The voltage drop at the dial is 0. Dial is off. The dial is off, there's no light. So in this way, you control which LED is on, which LED element is on, LED element is off. Any questions? Okay. So no question. So I have one example on the dial. Okay, I'll decide I will not rush that. Okay, so I will come back to the next class to discuss that. Okay. So any questions for the remaining class, the remaining time? Okay, I'm waiting. If you have questions, I can explain further.